We're going to talk about trigonometric identities, and it's kind of like proofs, but unlike geometry where you had to know the names of the theorems and all of that stuff, you're not going to have to write names of theorems. But you're still going to show algebraically, and using trig identities, you'll have two sides of an equation, one that has several trig expressions and one that has maybe one or two, or a couple. And you're going to work on one side of that equation and try to make it become or look like the other side of the equation. But you have to know your properties. Just like in geometry, you had to know your theorems to get there. But in geometry, you had to justify everything. Here, I'm just going to follow your work. You're going to show me an order. You're going to work down. Let's say you have an equation. Let's do this. You have some trig functions here. Why isn't it writing? You have some trig. There we go. Some trig functions. We'll erase it in a second. And some trig functions over here, and you're going to work your way down. And then if you need more room, you'll work your way over and then back down. So it's just going to kind of go like in a column, how you solve them. And you're going to try to make one side equal to the other is the goal. All right, let's get this cleaned up. Let's hope that I recalibrated my board earlier, so I hope that's not why this isn't. Oh, there we go. Whatever. All right, reciprocal identity. So you already know cosecant is 1 over sine. And secant is 1 over cosine. And tangent is, or cotangent is 1 over tangent. Well, the reverse is true for these, the reciprocal identities of sine, cosine, and tangent. This would be 1 over cosecant, 1 over secant, and 1 over cotangent. From our unit circle, you should be familiar, or at least be able to figure out the quotient identities. Because our quotient identities, tangent is what over what on the unit circle? It's the opposite over adjacent, but in terms of the height and length, it's y over x. But on our unit circle, y is sine and x is cosine. So this is really sine theta over cosine theta. That's one of the two quotient identities. Well, if that's tangent, then cotangent is cosine theta over sine theta. So those are our reciprocal identities. We use them pretty regularly. It's not writing again. Pretty regularly in trig identity proofs, and also our quotient identities. We use those pretty regularly as well. The next most common one that you're going to use is called Pythagorean identities. These identities come from the unit circle. Before we get to the unit circle, though, I want to talk about something because it's a little bit different than just regular numbers and regular functions. This, where see how the sine squared is on the word sine, is equivalent to me putting the squared on theta. Right, if I had sine squared, sine of theta squared. And it's equivalent to me just saying the whole darn thing, sine of theta is squared, squaring the entire expression. They're all the same thing. So it doesn't matter whether I put the squared on top of the sine, on top of the theta, or outside of the whole thing, those are equivalent. And that's not just true for sine, it's true for all trig functions, which is why I wrote this, that this would be equivalent to this. Trig theta squared, sorry, the pen's not working very well. Trig of theta squared. And then this last one is trig theta, the whole thing squared. They're all the same. They're all equivalent. So it doesn't matter where you put the squared. Normally we put it on either the theta or the trig function itself. It's the same thing. Speaking of squaring, we all know Pythagorean's theorem is? Yep. A squared plus b squared equals c squared. So we have our right triangle. We have it in the unit circle. In our unit circle, here's our height. That's y. And here's our length. That's x. And our radius when we look at any circle. But for our unit circle, y is sine of theta, if I put a little theta there, you can't see it, it's that little black dot. X is cosine of theta. And in the unit circle, why is it called the unit circle? The radius is 1. Now I was supposed to do that on the picture below, so don't worry about the picture below. I was actually going to, up here I was just going to write y squared plus x squared equals c squared. Not c squared equals r squared. But since y is sine, what that means is sine squared plus cosine squared equals 1 squared, and 1 squared is 1. So a squared plus b squared equals c squared. That's the height and length. And then c is the radius. Substitute in for y and x, sine and cosine. And for the radius 1, and you get our first Pythagorean identity. So our first Pythagorean identity is sine squared theta plus cosine squared theta equals 1. From this identity, we can derive 2 other identities using division, and then we can get other ones just from those. So in total, we're going to have 9 identities. I personally only memorize 3 of them and then just get the other ones as I need them from those 3. I have students who like to memorize all 9. They just like to know them. That's fine. You can choose which one you want to do. So to get this, we start with, let me slide it down a little bit, sine squared theta plus, that must be 9, plus cosine squared theta equals 1. And we're going to divide all of these by sine squared theta. So it's still equal. Well, sine squared divided by sine squared is 1. And cosine squared divided by sine squared, what's cosine over sine? Cotangent. So this is cotangent squared. And then 1 over sine is, so 1 over sine squared will be cosecant squared. This is another Pythagorean identity. And the reason I know it's a Pythagorean identity is because I see the squares. Whenever I see a squared on a trig function in a problem, I check to see if I can use a Pythagorean identity. Now the other one that we can get, if I start again with sine squared plus cosine squared equals 1. And this time, instead of dividing by sine squared, I divide by cosine squared theta. I can get, this will become tangent squared theta plus 1 equals secant squared theta. That dot there isn't supposed to be there. So these are the primary 3. Now you might choose to memorize them differently. This is the most common one that most people know, sine squared plus cosine squared equals 1. These other 2, you can memorize these or you can memorize another form of them. It'll be your choice. All right. So when I say how do I get the other ones? Well, I can get them if I start with these. So our first one we had was, this will give us a full list of them. Sine squared theta plus cosine squared theta equals 1. And then we had 1 plus cotangent squared theta equals cosecant squared theta. And we also had, sorry, what is it? Tangent, thank you. Tangent squared theta plus 1 equals secant squared theta. Well, during any particular problem that we're solving, we might not be given sine squared plus cosine squared. If we are, we can change that to a 1 because it's equivalent to 1. But I might be given cosine squared, and everything else is in terms of sine. And so I'm like, well, I know cosine squared is related to sine through this. For me personally, I would write this one down and then do what we're about to do. So if we had something that started out in terms of cosine, and we wanted to know what it was in terms of sine, well, I'd want cosine to be by itself. Cosine squared theta is equivalent to what? 1 minus sine squared theta. Like I said, I don't choose to personally memorize that, but some people do. And then this one, if I wanted to know what sine squared was equal to, because I was solving a problem that involved cosines and I really wanted to change this to cosine, or maybe there's some other trig functions, then I would look at, for me, I'd look at this one again and I would subtract cosine away. I'd have 1 minus cosine squared theta. So the other two you can either derive from memorizing the first, or you can just memorize all three. But they're all the same relationship, it's just the equation expressed in a different way. For the second Pythagorean identity that we know, I could solve for cotangent by subtracting 1 from cosecant squared theta. I could also solve for 1 by doing 1 equals cosecant squared theta minus cotangent squared theta. Some people just memorize this relationship because they want to know which ones are equivalent to 1, and then they work from there. It's up to you. And then the other one, if I want tangent by itself, I've got tangent squared theta equals secant squared theta minus 1. Or I could get 1 by itself, which then I would take secant squared theta and subtract tangent squared theta. If you have two trig functions that are both squared, then you might want these to make them go away and make it the value of 1. Otherwise, a lot of times we're going to have cosine squared and we're going to want to change it in terms of sine, or we're going to have sine squared and want to make it in terms of cosine, so we can use these to do that. So we'll come back to these in a minute as we try some problems, but we have just a couple other identities to look at. The next identity is the cofunction identities. So I'm going to start with a special right triangle, the 30, 60, 90 triangle. Here's my 30, so that's my 60 up there. Short leg 1, hypotenuse 2, long leg square roots of 3. What is the sine of 60? Sine of 60 would be what? Yes, square root of 3 over 2. Well, by the way, that's the equivalent to the sine of pi over 3, because pi over 3 radians is the same location as 60 degrees. So those are the same value. Now, something to note in this triangle, if I called this angle A and this angle B, they're complementary. These angles are complementary because they add to 90 degrees. So if I knew one of them and wanted to get the complement or find the other one, then I would do 90 minus 60 would give me 30, or pi over 2 minus pi over 6 would give me pi over 3. And it's important to note, you were supposed to learn this in geometry. Some of you did, some of you didn't. Sometimes it was just brushed over. But sine of A and cosine of B are the same. In fact, if you look at this, cosine of 30 degrees is the square root of 3 over 2. And so this will also be the cosine of pi over 6 will also be square root of 3 over 2. So all of these are equivalent. Sine of 60, cosine of 30 are equivalent. Sine of pi over 3, cosine of pi over 6 are equivalent. So what that means is if I have one trig function, by the way, this equation is, angle B, the measure of angle B is pi over 2 minus A, or 90 degrees minus angle A, the measure of angle A. So if I want to rewrite something in terms of its cofunction, so these two are cofunctions. In terms of its cofunction, I can simply do the following. I can say that sine of theta is equivalent to cosine of pi over 2 minus theta. Because that's what we have up here. Sine of 60 and cosine of 90 minus 60 are the same value. And so cosine of an angle is equivalent to sine of pi over 2 minus theta. So if you see any trigonometric proof identities that you're working on, that you're trying to prove, and you see pi over 2 minus theta in them, then you know you're going to come back and use one of the co-function identities. For tangent, its co-function is cotangent, so it would be equivalent to cotangent of pi over 2 minus theta. And cotangent would be equivalent to tangent of pi over 2 minus theta. For secant, it and cosecant are co-functions, so secant would be equivalent to cosecant of pi over 2 minus theta, and cosecant would be equivalent to secant of pi over 2 minus theta. By the way, this should also make sense in terms of the graph. If you think about the graph of sine and cosine, sine starts at 0, 0 and moves up, and it's up at its relative max at pi over 2, whereas cosine, if you're looking for its 0, its first 0, would actually be back here at negative pi over 2, and it would come up and that be at its relative max at 0. They're pi over 2 units away from each other. Same thing with tangent and cotangent. Those vertical asymptotes are pi over 2 units away from each other. Okay, so you guys probably, some of you remember even versus odd functions. When I think of even and odd, I think of even as being a parabola with its vertex sitting at the origin or somewhere on the y-axis. When I think of odd, I think of a cubic equation. It's an odd degree, and it does something more like that. Kind of like a tangent function, but not quite. A little bit different, because it doesn't have asymptotes. So even, and again, it's vertex at the origin. As long as it's, not its vertex, it's turning point at the origin. As long as it hasn't been shifted horizontally, and it's started out as an x cubed or x to the 5th or x to the 1st, as long as there's been no horizontal shift, it will be, and also vertical shift for this one, for odd, then it'll be an odd function, okay? And what it meant algebraically is for an even function, if you plug in the opposite of x, so here's x, here's the opposite of x, didn't matter what you did, you're going to get the same output. So it's still going to be equivalent to f of x. For an odd function, if this is x, and I put in the opposite of x, I'm actually going to get the opposite height. So I would get the opposite output than I would from regular f of x. Sine. Is sine even or odd? Sine is, so sine is like a parabola that would fold onto itself if I did a axis of symmetry right down the y-axis? No. Sine is more like the parabola, and where is if I rotated 180 degrees around, it would sit right onto where it was before. Sine is just like that in terms of what it does to the left and right as I go away. So this is odd. Cosine, however, could be folded or reflected across the y-axis, so it's an even function. Tangent, assuming note that there's no phase shift or vertical shift, is odd for its parent function. So knowing that, and knowing that even when you put in the opposite value, you get the exact same thing that you got if you put in the positive value. And for an odd, when you put in a negative input, you're going to get the opposite of what you normally would expect for the output. So even versus odd function, remembering that sine is odd. No, don't go wrong now. and that tangent is odd, and that cosine is even, I know that sine of negative theta, or the opposite symbol of what it is going to be negative sine of theta, the opposite. We'll talk about this in respect to the unit circle in a second. And its reciprocal function will follow the exact same rule. And the same holds true for tangent. Because it's an odd function, when you plug in the opposite of the angle, you'll get the opposite of the output. And the same holds true for its reciprocal function. So I want you to think about it in terms of quadrants. All students take calc, or a smart trig class, whatever you want to think. I don't need that right now. If I think about the restricted domains, even for sine and for tangent, right, we're between here and here. But this will be true for all of the unit circle as well. If I had an angle that was here, it would have a positive output, a positive height, a positive distance, if I had a positive angle in that quadrant. But if I do the opposite of it, and I was down here, then I'm going to have a negative height, which is going to create a negative output, because sine is positive up here, negative down here. Sine's also negative over here. And then the same thing with tangent. But cosine's a little bit different. Just think about if I had a positive angle. If I said positive 45 degrees, cosine square root of 2 over 2. Negative pi over 4. Well, cosine is still square root of 2 over 2. The x-coordinate is still positive. So when I plug in a negative function for cosine, I still get the same, or negative, the opposite angle, sorry, the opposite angle, then I get the same output I would expect if I had the angle initially. Secant, thank you. All right, so this brings us to some of these. And so once again, if I see any negatives in here, I'm going to try to remember my odd, even identities. Just going through the practice and making a list somewhere to help you study the identities will help you remember them. But if I see any negatives, I know I'm probably going to use an odd, even identity. If I see any squares, then I know I'm going to use a Pythagorean identity. If I see any pi minus 2 or pi over 2 minus thetas, I know I'll use a co-function identity. And if I see a bunch of trig functions, like there's a blend of tangent and cotangent or tangent and secant, I'm going to try to use one or all of their reciprocal values to try to simplify, but I try one at a time. So we have a couple examples here. With these, you should always, well, I'll give you a tip sheet on Monday. There's a lot of tips though, so you kind of learn them as you go too, but it'll be there for you to review. You start with the side that looks the most complicated. If there's a lot of fractions or if there's a lot of expressions on one side, then we want to start with that, because usually it's easier to try to condense that or do something with it to make it look like this side. So this side is locked in. We're not going to be having an equals as we do this. We're just going to show all of our work under the left side of the equation, because for this one, the left side has the most stuff going on. Well, I'm trying to make this look like secant. And I don't think well in terms of cosecant. Some of you will, especially after all of this. But I do know a different way to express tangent. How else can I express tangent? Sine over cosine. That's the quotient identity for tangent. Tangent and cotangent have a quotient identity. Now if I want, some people do leave this as times cosecant, and they know that sine and cosecant multiply to 1. But for most people, they're going to say, oh, well, cosecant is 1 over sine theta. Well, now it's as simple as knowing how to multiply fractions, which most of you are good at. This is going to go away, and I have 1 over cosine theta, which is secant theta. And since these match, we're good. We're done with it. We've shown that those are equivalent, that tangent times cosecant is equivalent to secant. So notice I worked down. If I were going to have more, if this weren't my last step, I would have come back up and then worked back down to do it in another column. This one, oh no, Mr. Ritter, I see factors there, yes. You're going to have rules of fractions from Algebra 2 and that we've reviewed a little bit in pre-calc. You're going to have factoring, all of those wonderful things, all the F words of mathematics. So we're going to distribute this to start. This one's not too bad. This is going to be 1 plus cosine of x. Distribute the negative cosine of x. Hey, that works out well. Look, negative cosine of x, those will go away. Minus cosine squared. By the way, I picked that side because it looked more complicated than the right. This side is locked in as sine squared x, and I want to get the other side to look like that. So, luckily, these two are opposites, so now I'm left with 1 minus cosine squared of x. I wonder what type of identity I'm going to use. Okay? Pythagorean identity. In fact, I don't even have to look, but you guys might want to look back and see which one I'm going to use. Now for me, I always remember, wait, if it's cosine squared or sine squared, I use, sine squared plus cosine squared is 1. And then I don't have to memorize all the other stuff. Well, that means if I subtract cosine squared, the answer to this is sine squared x. Some of you will just memorize that, right? That 1 minus cosine squared is sine squared. And as I practice it, I'll remember it better too, and my mind will just jump to it. And these are a match, so I'm good. Any questions on that? Yes?
So there's really like no answer, you just have to show me what it is.
So yeah, when you do this, you already have the answer. And here's the other bad thing. For some of these, there's more than one way to do the problem. And when we get to the last example, I'll show you the way I want you to see, so you can see what to do with the fractions. But in third hour, we actually started it a different way because somebody said, oh, I see this, we could use this, and they were right. But it worked out completely different. That's why it's important, especially for when I'm grading your quizzes and your tests and checking in your Guppy, Minnow, all the different levels, that you show your work going down and then over if you have to, so back up to the top and down so I can follow what you did step to step.
And will it always equal it?
It will, as long as they're right, and for everything that we have mapped out and planned, they are. Now there's something on here that has a wrong sign, and when we get to it, I'll make sure to tell you to fix it. So here's another example. Obviously, I'm going to start on the left side because the right side looks a lot easier. The left side looks a lot more complicated. And what I did earlier was I tried to factor right away, I think, except it didn't work out so well for me. So, by the way, this is going to be trial and error. When you go to do something, sometimes what you think won't work, and then you got to try something else. So what did we do instead? Oh, wait. Oh, jaw. Okay. This. Somebody already knows, some of you already saw this. I thought somebody said this right here. What do you notice about those two functions? Those are reciprocals, right? So they're going to be 1. So this is really 1 over sine times sine, which over 1, which is just 1. They don't, when they cancel, there's a 1 there through the multiplication. Whoa, what am I doing? So I still have to bring this, still have to bring this part down, so that's minus sine squared theta. By the way I did it earlier, started it earlier, would have worked, but it would have been a lot more complicated. 1 minus sine squared theta, that should look familiar. It's a Pythagorean identity. In fact, it is the equivalent to cosine squared theta. So those are good.
Thank you.
In the next problem, I know an identity right now, so you're like, whoa, what's that crazy thing inside the parentheses? Wait a second, that looks familiar. It's not a Pythagorean identity, it's not a reciprocal identity, it's a co-function identity. And cotangent is a cofunction with tangent. So I know that this, oh, I don't say what it's equal to. I'll tell you in a second. This is equivalent to tangent, so this will be sine of x over tangent of x. This was supposed to be equal to cosine of x. I forgot to put it on your sheet. I wasn't sure what it was going to equal, and I had to solve it, and I forgot to go back and fix it on yours. So I'm not done, though. What can I do with tangent? Rewrite it as sine over cosine. So I have sine of x all over sine of x over cosine of x. Well, to divide by a fraction, I need to multiply by its reciprocal. So really, this is sine of x over 1 times cosine of x over sine of x, which is just cosine of x. Questions? Only a couple more to go. Oh, you still needed it? Yeah. Still need it? Yes. Great question. It's a required part of the pre-calc curriculum. Across the United States, there will be places where you have to do that. In higher levels of mathematics, you do have to prove, and it's going to be algebraically like this, using identities, using all way beyond this. I know. No, there's an answer. This is the answer. When you're trying to prove things like, hey, this is going to work out to this, you've got to show the logic step by step. And it depends on what you go into. A lot of things, no, it's not going to be this rigorous, but certain fields will be this rigorous. So, not most of them. All right. So here we go with this example. I noticed right away in this problem, there's two identities that I believe I'm going to use. One of them is Pythagorean identity, because I see the squares. In fact, secant squared and tangent squared, huh? We're not cloning it today. Wonder what identity that is. Wait a sec. It's equivalent to? No. It's equivalent to what? 1. Yes. Because 1 plus 1. 1 plus tangent squared is secant squared. So if I subtract tangent squared, then together, by the way, I've done this before where I didn't recognize that, and I actually changed secant squared or tangent squared. Well, then in the end, it still worked out to be 1 because stuff subtracted away. And I can show you that in a minute. So that's 1. Had I done this, had I replaced tangent squared, because that's what some of you would have thought of, oh, let me replace tangent squared with 1 minus, or secant minus 1. Secant squared minus 1. Well, when you distribute the negative, what happens? The secants are going to cancel out because you got a 1 positive, 1 negative, and the 1 becomes positive. So you could do it that way, you would still get the same answer. So those two become 1 right here. This becomes 1. So now I have 1 over cosecant of the opposite of x. Oh shoot, that opposite thing. That's a even odd identity. And cosecant is with sign, that's an odd identity, which means it's going to be the opposite of what I see. Negative cosecant x, or negative cosecant theta. Well, that's not what I'm supposed to show in the end, but I do know that this is really just sine. So it's negative sine x. Got this side to match what or got my work to match what's on the right side. So this is using multiple identities, using the Pythagorean identity, using the odd even identity, using the reciprocal identity. The next one has one of those fabulous F words of mathematics. Guess what we're going to do? Factor. Sometimes factoring helps, sometimes it doesn't. Give it a shot. If it doesn't work, you go back to it if it makes it easier. In this case, it does, because when I factor out sine squared x, I'm left with cosine squared x minus 1. And cosine squared x minus 1 looks familiar. Now here's the thing. Some people would say, well, can I change that sine squared to 1 minus cosine squared? And I'm like, you could. But then you're trying to get your answer in terms of sine, so that's probably not what you want to do. This looks familiar, but it's not quite right. Because sine squared plus cosine squared is 1. If I'm trying to find sine squared, it should actually be 1 minus cosine squared. I have the opposite in there. So factor out a negative 1. So if I pull out this out as negative, this becomes negative, this becomes positive. Now this is really negative sine squared x by 1 minus cosine squared, which is sine squared. Because that's the identity right there. Sine squared is 1 minus cosine squared. Well, I'm supposed to multiply these two, so this becomes negative sine of x to the 4th, or sine to the 4th x, which is what I was supposed to prove. I've had people who did this problem without factoring first. You really do need to factor this one first. They've tried other stuff. They've gotten everything in terms of cosine. That works. Then you got to convert it all back to sine. It takes a lot longer. So when you do this, you need to know which identities you're using, but you also need to keep in mind where you're going. Because if I change that stuff to cosine, then I would have then had to change it all back to sine in the end anyhow. This one, this is where sometimes if you have a giant fraction, it helps to split the fraction up. And sometimes if I have two expressions and one of them is a fraction, it helps to put them as one fraction. So we're going to try to do that right now. I'm just going to show you one of the techniques is to try and make it into one fraction. And sometimes it works, sometimes it doesn't. So we're going to multiply this 1 so that we can get it to have the same denominator of 1 minus cosecant of x. I got to multiply the top by 1 minus cosecant of x too. Because 1 minus cosecant of x over 1 minus cosecant of x is 1. Well, this is going to let me get it to one giant fraction, because now I have 1 minus cosecant of x plus cotangent of x squared all over 1 minus cosecant of x. So I'm going to go, how did that help you, Mr. Ritter? Not yet it didn't, but I do know that this kind of looks like something I could factor if they were the same term. Doesn't mean I'm going to factor it, but there are times when I factor. So what I'm going to do is I'm going to look and say, wait a second, this has got a squared. And we have a relationship for cotangent squared. Cotangent squared is really cosecant squared minus 1. So I'm going to bring it over here because I'm running out of space. You might be too. So I have 1 minus cosecant of x plus cosecant of x squared minus 1. And that's still over 1 minus cosecant x. Now I've had people before who are confused about the algebra and division, and they think we can just cancel the 1 and the cosecant here. Can you do that? No. Only when everything's in factored form in the numerator. I can't do 2 plus 3 over 3 and cancel the 3. That's not 2. That's 5 over 3, which certainly is not 2. Now, if it was 2 times 3, if they were all expressed as factors, then I can cancel them. And that's when you guys did all your gripings from having the gold level, right? Gold, bronze, right? So we're kind of back to that now. But this is a little bit better. It works out nicer. Anyhow, when I distribute this, wait a second, isn't this 1? this is minus 1. Those are gone. So I now have cosecant x plus cosecant squared x.
Wait, why is it the negative in front of the cosecant x?
Wait a second, it might be. Did I write the wrong thing down? Was it supposed to be 1 minus cosecant squared?
No, isn't it negative?
No,
secant x
because it's 1 minus cosecant.
Oh, it's 1 minus cosecant squared x?
Well,
And here.
No, your first thing.
This is 1 minus. So this is, oh, so this
Yeah,
is negative.
yeah.
Yes, thank you. Yep, you're right. I want to do like I did, miss the sign, and you'll get to the end and go, wait, why is my sign wrong? Or maybe worse, if it wasn't near the end yet. All right, now, any ideas what we're going to do? Because I can't cancel anything. Gonna have to what?
Bye.
Oh, I thought somebody was going to say. I can't divide yet unless they're in factored form. So another F of mathematics, we're going to have to factor. Well, I'm going to pull out, I could pull out cosecant. Let's take a look.
Pull cosecant x.
Cosecant of x, it is going to work. So I have negative 1 plus cosecant x when I pull that out, right? I factored out cosecant. That makes this part 1, this part cosecant. And this is all over 1 minus cosecant x. Uh-oh, those don't look the same. What do I do? If I pull out a negative cosecant instead, this becomes positive 1, this becomes negative cosecant x, which is the same factor. The 1 is positive, the cosecant inside is negative. I could rewrite it if I want to. Then I wrote the wrong trig function down. Hold on. Oh, no, I didn't. This is the one that I told. Remember I told you earlier there was one I had written down wrong? Oh, that is the same thing. I don't need to rewrite it. It's even the same order. So these cancel now that it's multiplication, not addition, separating those. And I'm left with negative cosecant x. This is the one where, and you can look right there. What does it say right here? Make negative. So I forgot to tell you that I wrote down the problem wrong. There should have been a negative on here to start. That won't happen on your guppy and all that stuff. Those are correct, the way they're supposed to be. So you've picked up 2 things. One of them is the guppy worksheet. If you want to get a head start before Monday. The other one is 10 problems I'd like you to try in class today and take them home and work on them. We will go over them on Monday. Any questions you have? So you know what the answer is already. You're trying to work toward it. If you get frustrated with one, go to a different problem. Come back, try a different approach later. Let me stop this and I'll come around and answer any questions. Well, there are 4 levels, and they are due in time to do the quiz review, or the BA review, and take the BA on this. So, let me stop this.